As you can see from the title of this lesson, this tutorial is about analyzing data. This will go in your regular notebook, but this entire section that we're going to look at here is all going to relate very directly to laboratory experiments and experimentation. I call this analyzing data, but most often when we're talking about looking at and analyzing laboratory results, we will do something with percent error, which is also going to be discussed during this tutorial. If we take a look at the data that we've discussed so far, you'll find out that there are two predominant terms that we're going to have to discuss the difference of if we want to analyze our data. There are two types of data. There are qualitative pieces of data, and remember, qualitative meaning quality, no numbers, and then there are quantitative data pieces, and a quantitative, quantity, meaning involves numbers. We're going to address both of those as we go through these. The two terms that we're going to have to be able to distinguish between is that of accuracy versus precision in data. By definition, accuracy is talking about the closeness of a measurement to an accepted value. Like for instance, if I were having somebody trying to guess, the weight of a professional fighter, if I know the fighter's weight is 220 pounds, however close to 220 their guess is going to tell me how accurate they are. Precision, on the other hand, isn't the closeness of a measurement to the real value, it's simply the closeness of measurements to each other. Very often in lab, we won't just do one trial of an experiment because we want to be able to repeat things over and over again to be sure that we have the best information at our disposal that we can. So if I were going to be fair with the analogy of a boxer and guessing the weight, I may give you 3 chances to guess the weight. If we know he's 205 and you guess 3 times, the accuracy is how close you are to 205. The precision is how close together your 3 guesses are to one another. To give you a visual representation of this, what I have up here is a little depiction of, say, a target. Right? And if we do this in class, what I usually do is I have 4 different people, person A, person B, person C, person D, take a tennis ball or a dart or something along those lines and throw it at a target. So what I've done for the purpose of the tutorial is I have presented what those results are often. Whenever the people throw, we get a variety of different things. Person A, for instance, were our blue X's. Right? They threw 3 times. All 3 of them were over here. Person B was the red circle. They threw 3 times. 2 were here. 1 was out here. Person C, they threw 3 times. They were the triangles. They threw 3. They are all right there. And person D also threw 3 times. Those are the brown diamonds. 1 is here, 1 is here, and 1 is here. And that is their 3 throws. So what we want to do is we want to analyze if these particular individuals' data are accurate, precise, both, or neither as we go through. So if we look at person A threw these 3 darts, so to speak. The X right here in the middle is our target. That is the correct location that we wanted to hit. So if we looked at person A and said, are they accurate? Are they close to the accepted value, which is the X? The answer most likely would be no. They didn't get in the inner circle. They didn't get into the second inner circle. They barely got into the third most inner circle. So they are not very accurate. Now, we would check for precision. Precision is the closeness of their measurements to each other. If you notice, 1, 2, 3 X's, all 3 of these X's are very close to each other. So even though they are not accurate, they are precise. So it's not accurate, it is precise. Let's look at person B. Person B is our red circles, right? 3 throws, 2 of them were here, 1 of them is here. We would say, are they accurate? Are they close to the X? 2 of 3 throws hit in the innermost sector next to the X. So I would say, yes, they are pretty accurate. A large majority of their data was very close to the accepted value. So we would say that they are accurate. Would we say that they are precise? Well, we take a look. Are the 3 throws close to each other? 2 of them are. 1 of them is not. And if you look at the accuracy, I said it was accurate because 2 are really close, and the third is still just 1 sector away. So on the whole, all 3 are in the second most, 2 of which were in the innermost. We'll say they're accurate. In terms of are they precise, 1, 2, yes. The third is farther out. I would say that this is not precise. Third person, person C, is our green triangles. What do we say if the person is accurate? Here's our desired target. 1, 2, 3 of them right next to our desired target. Absolutely, we would say that they were accurate. And then, would we say that they are precise? 3 throws, 1, 2, 3 throws, all right next to each other. I would also say that they are precise. Our last person, person D, is our brown diamonds. Are they accurate? Here's our desired target. Here's 1, here's 2, here's 3. Only 1 of the 3 throws made it into the target area at all, and the 1 is in the outermost. So I would say that they were not accurate. Would we say that they are precise? 3 throws, 1 was here, 1 was here, 1 was here. Those are very far spread out, so we would also say that they are not precise. And this is a way that we analyze qualitative, meaning no numbers, you don't see any, data. Right? Is it accurate, meaning closeness to the target? Is it precise? Are they close to each other? And hopefully this helps to highlight what's going on with that. So if that is how we tackle qualitative data when we don't have numbers, how is it we analyze data whenever we do have numbers, quantitative data? And that leads us into a discussion about something called percent error. And percent error is a quantitative method of measuring accuracy of an experiment. Next to quantitative, I have the number sign in parentheses to remind you quantitative data is numeric data. So percent error is our numeric way of analyzing number-driven data. There is an equation for percent error. It is listed right here. Percent error is equal to the accepted value minus the experimental value divided by the accepted value times 100. Just to make sure that everybody is clear between the accepted and the experimental, the accepted value is already determined. A group of scientists, right, known as the IUPAC, right, International Union of Accuracy and Measurement Precision, perhaps? I'll get back to you. I'll check on that. Right, but the accepted, right, value is already determined and it's listed in chemical handbooks. You can look that up, or most often I will give you what the accepted value, right, for a particular measurement would be. The experimental is your data. You go back into the lab, you conduct an experiment, you measure things, whatever your number is that you determine, that is your experimental. So you take the accepted minus the experimental over the accepted. That gets tedious to write, so most often when I ask you what is the percent error equation, most people will tell me percent error, percent E, is A minus E over A times 100. And you have to remember that A is accepted and E is experimental. So let's take a look at two examples where we are going to calculate the percent error given some number-driven data. You can print your own of the question out off of the handout section here in Chapter 2, but I also have written them up here. So if you already have them printed out, just transcribe them over into your notebook and then follow along with the answer that I do. Or if you haven't, simply copy down as I read what the question is. Example 1 says, a student measures the mass and volume of a substance and determines its density to be 1.45 grams per milliliter. The actual density, or the accepted density of the substance is 1.40 grams per milliliter. What is their percent error? What is that student percent error? So, if we are going to do a percent error problem, we need to start with the percent error equation. Percent E is equal to A minus E over A times 100. Now, the important thing here is to decide which of those numbers is my accepted, which of those is my experimental. And if you take a look, the difference that you're looking for is which of those numbers was given to me as the definitive value and which of them was the one that I gathered from the laboratory. So if a student measures the mass and volume of a substance and determines its density to be 1.45, because the student has done that, I'm going to call that the experimental. The actual, and actual is another word for accepted, is this. That must be my accepted value. So if we're going to plug in and solve here, I would say percent error is equal to my actual, which was 1.40 grams per milliliter, minus my experimental, 1.45 grams per milliliter, divided by my accepted 1.40 grams per milliliter times 100. Only thing here that could possibly trip you up is a Sig Fig issue. Whenever you're working with these problems, if you have a subtraction on top and then you're dividing, you have to do the top of the parentheses first. And this is where some people would get tripped up. Right? If I do that subtraction first, I would say that the percent error is equal to, so 1.40 minus 1.45 is going to be negative 0.05. Now, if you take a look, we have to remember our rules for Sig Figs. When I'm adding and subtracting, I care about places past the decimal. So if I'm going to look at the answer, 1.40 goes 2 past, 1.45 goes 2 past. That means the number off of my calculator, which is 0.05 negative, can also go 2 past. So the 0.05 has to stay written just like that, which would be grams per milliliter. That's still getting divided by 1.40 grams per milliliter times 100. Now, this turns into a different Sig Fig problem because we are no longer adding and subtracting, we are multiplying and dividing. And the rules for Sig Figs change. When I multiply and divide, I simply care about numbers of Sig Figs. So if I put this into my calculator, negative 0.05 divided by 1.40 times 100, my calculator tells me negative 3.5714%. I need to decide how to write that. So if I take a look, I look at my Sig Figs. Dividing means I care about number of Sig Figs. 0.05 only has one Sig Fig because in a decimal those first zeros don't count. So 1 Sig Fig here, 3 here, means I only get 1 Sig Fig in my answer. So is a 3 significant? You bet. There's my 1. Now I have to decide about rounding. There's a 5 after, which means we have to go to that separate set of rules. First thing we check if there is a 5 is, are there any numbers after it? And if the answer to that question is yes, which there are, that always means that we round up in terms of what we are doing, right? Which means the 3 will become a 4. So negative 4% would be my percent error for this particular problem. As you take a look, 2 things I want you to understand. 1, is it okay to have a negative sign? Absolutely. Right? You can get a negative sign for percent error. Don't let that throw you off. Right? The negative simply means that the experimental number was larger than the actual or the accepted. Like, that doesn't mean it's any more or less wrong. And that's the second point. It's the number value that tells me how accurate I am. A negative 4% error is better than a 5% error, because the larger the number, the larger the error. The negative just tells me if I was too high or too low. Right? So it's the number. So negative 4, right, is the same percent error as positive 4. So you don't let that throw you off as you go through it. Right? So the percent error there would be 4%, right? And that is a pretty good percent error. Second one looks like this. It says, what is the percent error for a mass measurement of 17.7 grams, given that the accepted value is 21.2 grams? Right? Again, if I see what is the percent error, the first thing I want to do is jump to my percent error equation. Percent E equals A minus E over A times 100. Then we want to go up into the problem and determine what is the experimental, what is the actual. So it says, what is the percent error for a mass measurement of 17.7? Doesn't really tip its hand at all there. Given that the accepted value is 21.2, and that phrase tells me that the 21.2 is the accepted, therefore 17.7 must be the experiment. So now we go ahead and plug in. Percent error is going to be equal to A, which is 21.2 grams, minus E, 17.7 grams, all over A, 21.2 grams, times 100. From here out, it's a math problem, but again, you have to watch your Sig Figs as you go through. Right? So if we do the numerator first, right, your 21.2 minus 17.7 is going to give me a value, right, in my calculator that says 3.5. Right? The question becomes, am I able to write it that way? Right? We are subtracting, so we care about places past the decimal again. 21.2 goes 1 past, 17.7 goes 1 past. That means the answer can go 1 past, so I'm allowed to leave 3.5 as 3.5. Still put the 21.2 grams there on the bottom, times 100. Right? Grams will cancel, that's why our percent error is always units of percent. I take 3.5 divided by 21.2 times 100, and my calculator said 16.5094. And then I have to decide my Sig Figs. We now jump into multiplying and dividing, so I care about the number of Sig Figs. 3.5 has 2, 21.2 has 3, so my answer has to match the least, so I get 2. Does a 1 count? Yes. Does a 6 count? Yes. There are my 2. I have to round. There's a 5 after, so we pivot back to our rule of 5. Is there anything after the 5? Yes, which means the 6 will round up. Therefore, this will be a 17% error. You'll find that the percent error when you guys do labs will tend to be relatively high, because you have to keep in mind that you've never done a lot of these experiments before. There are people that have done these 20, 30, 40, 50 times, and they will still get like relatively large percent errors. Like some experiments lead to higher percent errors than others, and we'll talk about why that is. Right? But don't let your percent error get you down as you go through lab experiments. Right? The biggest thing I want you to understand is it's just important that you understand to get your percent error. And what you'll find is the longer that we get in lab, you will start to see those numbers decrease and decrease and decrease as you get more comfortable working with the different chemical equipment and different types of experiments that we'll do. I hope this helps out with anything we do. If you have any questions, as always, feel free to stop it.